Hello, everybody. It's my pleasure today to introduce one of our new faculty members to give the seminar. Melisa joined us in August-ish. Uh, uh, she has done some really neat work with haptics and educational contexts, and a lot of do-it-yourself types of systems. I would encourage all of you to, at some point when you get a chance and everybody's back on campus, to find her in person and talk with her about her work and check out the systems and things like that. But this is your chance to kind of get a preview for that when we finally do get to all see each other again. So without further ado, take it away.
Thank you, Aaron. So as Aaron mentioned, I'm a new assistant professor in the RI. My name is Melisa Orta Martinez. And today I want to talk to you about some of my work in the design and analysis of open source educational haptic devices. If you watch my job talk, it's going to be pretty familiar, but I'll do my best to make it entertaining again. um, so, all right. So during this talk, I'm start by motivating this work with a brief definition of haptics and haptic devices, because I feel like a lot of people are not really familiar with haptic devices. And I will introduce also why it is interesting to study haptics in the context of education. And I will present 3 different devices for educational applications and how we have applied them in the context of education. These are Hapkit, Haplink, and HapCaps. And finally, I will conclude this work and talk about some future directions. Yep. So first of all, so what is haptics? So haptics is our largest sense in our body. It's our touch sense, and it comprises all of our skin. And it helps us feel things like temperature or touching an object, but it also enables us to move. So if I just point my arms out in space and I can do tasks like touch my 2 fingertips above my head, which you can't see in the camera, but I can do it without really looking or thinking about it, thanks to all of the different mechanoreceptors that I have in my skin or in my muscles that enable me to move. So as you can probably tell, our sense of touch is pretty involved in most everything we do. And because of that, the field of haptics is incredibly broad, and it comprises fields such as neuroscience, robotics, psychophysics, and there's still a ton that we don't know about the sense of touch and haptics. There's a lot of questions about perception, about different applications that could be applied to the sense of touch, how to best design these devices and control, and how to best render all these virtual environments. And as an engineer, what I'm mostly interested in is in the design of these different devices. And so a haptic device is a device that will enable interactions through the sense of touch with, for example, a virtual environment. And these virtual environments are sometimes rendered through the computer with graphics, but they don't have to. So the haptic device can also be pretty standalone. And in general, there's 2 different types of haptic devices. On the one hand, you have kinesthetic haptic devices, which will render forces through a tool. And on the other, you have tactile haptic devices, which will directly stimulate the skin. And of course, there's combinations of the 2. And I just want to show a quick example of a commercially available kinesthetic haptic device, so you get an idea of a device that's available that can do haptics. And so what this device is doing is it's allowing the user to interact with this virtual dessert or flan. And as you can see, you're really interacting with the dessert through a tool. And so what you're going to feel is kind of the stiffnesses and other surface properties, but through something else. So you're not going to directly feel the moisture and the texture in your fingertips, but instead it's going to feel as if you interacted with it through something like a pencil, right? And so as you can see, this is one of the most available haptic devices. As you can see, there's still a lot of work to be done in creating better haptic devices that do give us the sensation of actually the moisture and the temperature and the richness of all the textures that you will feel when you interact with real objects. But even with what we can do, there are still a lot of applications that have benefited from using these type of devices, and applications such as, for example, in medical surgery, in rehabilitation, in surgical training, even gaming. A lot of us have controllers with different vibrations, right? And even in improving car safety. And the application that I've been mostly interested in researching is in education. And the reason for that is that as we're growing up and learning, we do a lot of this learning and exploring through our sense of touch. However, at some point, we decide that this should be our learning model. And because of the way we have decided that we should learn, there's been a lot of research conducted into how we learn with the sensory modalities of sight and sound. But there's not been a lot of research conducted into how we learn with the sense of touch. And those studies that have been conducted have actually, I'm so sorry, it's just my cat. Go away. And, and those studies that have been conducted have given us conflicting results. There's been some studies that have predicted that haptics does allow us to learn by providing an additional cognitive channel. And there's other studies that have actually said, no, haptics makes no difference. And there's other studies that have actually said that haptics actually inhibits learning. However, I do find some of those studies a little problematic in that most of them are done in this way, in which you have some commercially available haptic device or some very specialized laboratory equipment in a laboratory, and these studies are done as interventions over a few hours, as opposed to being done in more traditional learning environments across several age groups, and using devices that can be customized to the study that you want to do. So as I mentioned, these studies are inhibited. Like, I'm not faulting the researchers at all, not even a little bit. These studies are inhibited by just the availability of these haptic devices and what's out there. And most of these haptic devices are really expensive, and so you can't really deploy them in a school or in other diverse educational environments. And also they're pretty specialized and they don't really allow for customizations. And so my work has focused on how to design these haptic devices that are open source and inexpensive in order to be used in classroom environments. And I've also conducted experiments into the role of haptics in education. And the idea is to understand how the mechanical effects of these simple hybrid systems will affect performance, perceptions, and the creation of haptic illusions. So now I will first start by introducing the first device, which is Hapkit. And Hapkit is an open source kinesthetic haptic device that's designed for students who have had a minimum of high school physics, so they're non-calculus based, so about juniors on. And here we'll present how the design of Hapkit evolved from lessons learned in several educational environments and how those design changes affected the mechanical performance and perception. Now, first, I want to show you a little video of Hapkit being used. This simulation was programmed for a class on controls class, university controls class. And the idea is it's programmed as a PI controller. So as you can see, as you move the device away from the center point, it returns from the center point in a manner that mimics and feels like a PI controller. Then this other simulation is showcasing teleoperation. This was for a robotics class. And the idea is that these two devices are now virtually going to be tied together. And if you move one, then the other will move in accordance, and you can feel what the other device is feeling. And so Hapkit was created with the idea of building a haptic device that should not just be laboratory or university equipment, and instead it should be a device that would enable students to manufacture and assemble it themselves. And for that, it needed to be low cost, open source, and made of components that students could acquire easily. And so when I came into the project, the first version of the device, Hapkit 1.0, had already been designed, and it had been designed specifically for an experiment where we made an online class and the devices were shipped to the students as kits, and then they assembled it themselves. And so some of the main features of the device is that it's made out of pieces of acrylic that have been laser cut. It has a friction drive, and it uses a pretty good, expensive motor, a Maxon motor, which typically runs for about $300. And so for the next version of the device, what we wanted to do is now open up our online class so that anybody could take it. But for that, we needed to not ship the devices to the students. And so we wanted to find a design that now students could actually manufacture themselves, and we didn't have to ship them anything. And so that brings us some design considerations. On the one hand, for manufacturing and assembly, we needed to design something with a minimal number of parts, so not so much assembly, because we couldn't really give personalized attendance to all of the students if there were going to be thousands of them instead of just 100. We needed an unambiguous and robust assembly process. We needed to design something that was, well, the parts were low cost, but also that could be manufactured with low cost manufacturing methods, because we wanted the students to manufacture the device themselves. And we also wanted to design something that was uncovered so that the students could witness all of the different parts interacting with each other and learn more that way. However, all of those considerations conflict with the rendering considerations that you need to be able to do a good haptic device. And in this case, we're talking about specifically impedance type kinesthetic haptic devices, for those of you who know haptic devices. And so for those type of devices, you do need to have a device that's back drivable. You need to have a device with low friction, moving parts with very low inertia, and you also need motors with low Cogging torque, which is why usually these haptic devices are very expensive, and they're made with very expensive motors. And so for the next iteration of the device, what I designed was something that now was 3D printed so that students could manufacture it themselves. And we did find a motor that was pretty cheap, but that does have some unwanted characteristics. And I will talk about the analysis of those characteristics in just a little bit. And as you can see, the design of the device is pretty similar to the device that we had before, and still uses a friction drive transmission. And so over the course of a year, we tested Hapkit 2.0 in several educational environments with hundreds of students. We used it in a massive open online course on haptics. We also used it at Stanford in university and so in undergraduate and graduate classes on haptics and controls. And we even did a 2-week workshop in a middle school classroom. And through that whole year, we had a lot of learnings about the design of the device and how to improve it. From part of what we learned was that even though our device could be 3D printed with high-end 3D printers by us, if you try to 3D print it with a low-cost 3D printer, there were a lot of problems with warping, and it had several effects. Number one, it made the parts pretty brittle. So for example, in the middle school classroom where students are not so careful with their devices and they get knocked off desks a lot, then the devices would break pretty frequently. And then the other problem was that the paddles wouldn't really print completely circular, and then you wouldn't have a consistent feel throughout your workspace. And then from the online class, what we learned is that the friction drive really wasn't adequate, because the friction drive, as you can see, it has some bar for adjustment so that you can adjust the amount of friction that you have between your drive wheel and your paddle. And trying to explain somebody online how much friction and how to adjust it and what the right feel of the device should be, it's impossible. And so we needed something where you just assembled and it was ready to go. And so all those learnings drove the design of Hapkit 3.0. And as you can see, now we designed it with a more rounded design everywhere to prevent warping with low-cost 3D printers. We also added suction cups so that it wouldn't get knocked off desks. And we took advantage of the customizability that's possible with 3D printing. And so we designed it in 2 parts. Now you have the handle, which slaps into the sector. And so the students are free to modify their handle and make it their own. And we found, I'll talk about this in a little bit, but we found great outcomes in graduate classes, specifically where the students were very creative in manufacturing their own handles. And we also felt that way students would take care of their devices a little bit better and not knock them off. And then finally, we went back to a more robust capstan drive transmission. So traditionally, haptic devices usually use a capstan drive. However, for educational haptic devices, people have chosen to use a friction drive just because of how painful it is to assemble a capstan drive. And so what we did instead is design a new mechanism to make the capstan drive easier to assemble. Okay, so now we have 3 different designs of a device, and we now need to quantify the differences between them and try to quantify their performance. And so the first thing we did is we made a linear model, and we fit, so a linear model, sorry, of the structural components. And we used a frequency-based method to fit parameters to that linear model so that we could quantify the differences between the structural components. And this is the results of that experiment. And so some interesting points from the results is that the model does say that the Hapkits 1.0 and 2.0, which use a friction drive, do have a higher damping coefficient, which is that's good model. And then the things that are interesting here that the model doesn't really capture are the non-linearities of the friction drive. We're just fitting a linear damping term, but that doesn't really capture non-linear effects that can be seen as a phase shift in the body plot. And so now the next difference between the devices, as I mentioned, is that one of the devices uses a very high-end motor, and then the other device is a pretty cheap motor, which has some non-wanted characteristics, mainly cogging torque. And so now we needed to characterize what that cogging torque was. And so we made this setup in which you use a very high-end motor to drive the housing of the low-end motor, and then to the shaft of the low-end motor, you're going to hook up a force torque sensor, and then measure what the forces are as a result of just spinning the housing of the motor. And you can see here one run of that experiment. And you can see that we can see 6 peaks of the Cogging torque, and that makes sense because the motor is going to have 2 poles in the magnet and three preferential positions in the 3 teeth in the magnetic core, and so that gives us 6 preferential positions. And then down here we can see in this plot is now for the mean and standard deviation of the peak-to-peak amplitude of the Cogging torque measured at different frequencies and for different speeds of rotation. And so when a user is using Hapkit, they will typically move the handle with a speed between 2 and 5 centimeters per second, which results in a motor rotation between 10 and 30 radians, 10 radians per second, and a peak-to-peak Cogging torque between 1.2 and 1.5 Newton millimeters. And that can be seen as a force of about 0.3 newtons at the handle. And so that's something that a user can definitely feel. So then the next step is to try to understand what the effects of that force that the user can feel is going to be in the rendering of virtual environments between the 3 devices. And so for that, in order to understand how that will affect that, we now performed a stiffness discrimination test. And so what that is basically, it's a user study in which we used 14 participants. And what participants did is they performed a stiffness discrimination task using a force choice paradigm with the method of constant stimuli. And what that means is that for each Hapkit, for each participant, participants will perform 100 spring comparisons with a reference stiffness. So you will present the participants with a reference stiffness, which in this case was 16 Newton meter. And then you present them with another one and you ask the question, which one felt stiffer? And then to that, you can fit a psychometric function. And based on that psychometric function, you can calculate your just noticeable difference and your Weber fraction. And so in this plot, you see the different Weber fractions for each device, for each user in the user study as dots. And you can also see the mean Weber fractions. And so what the Weber fraction tells you is the minimum amount of stiffness change that a user will be able to feel. And so less Weber fraction is better, because that means that you can render more distinct springs with that device. And so as you can see, Hapkit 3.0 has a smaller Weber fraction than the other two. And then we ran a two-way ANOVA test, and that also showed that Hapkit 3.0 was statistically different from the other two. And so that was a good thing and pretty surprising, because for this particular experiment, what that means is that then friction dominates the results. So you have 2 devices that present with Cogging torque, and 2 devices which have a friction drive transmission. And then from the experiments, you can tell that the friction is worse for rendering the springs, and that was pretty surprising. Okay, and then so lastly, I just want to mention that Hapkit 3.0 has been used since 2015 in graduate classes at Stanford and undergraduate classes, as well as in the massive open online class that my former advisor runs. And perhaps the most surprising thing that we have learned from using the device in all of the different classes has been how much students really enjoy that customization aspect of the device and how creative they are in creating their own devices with using that customization. So in the Haptics graduate class in particular, it has a pretty large project component at the end of the class in which students have to create their own haptic applications. And a lot of students choose to create their haptic applications through further customizing their device. And here's an example of one of those customizations in which a student chose to model the piano and the harpsichord, the feel and the sound of it. And then they changed their device so that they could now render the feel and the sound of a piano and a harpsichord. And it was a pretty cool project. Then I just want to mention another type of application that we have explored using these devices, and that is in teaching not just schools and not just classes at universities and graduate and undergraduate classes, but also just in schools for STEM learning. And this is an example of something that can be taught with the device. And in particular, this is a lesson on springs. And so what the students were able of doing is to add different springs together in parallel and in series, and then they can feel the result of their experiments using the Hapkit. another type of use also for STEM learning is now instead of rendering something in physics that exists, but instead trying to render abstract mathematical concepts and to aid in grounding these mathematical concepts in embodied interactions. And so this particular simulation is a simulation on trigonometry in which users can drag and drop different functions of sines and cosines, and then they can change the frequency and amplitude of those functions, and they can feel the result of what they're doing. And so for testing this new way of abstracting mathematical concepts, what we did is we ran a small design study with just 2 pairs of students in which we didn't show them this graph. So they couldn't really see the purple. They could play with everything in the sandbox, but they couldn't really see the graph. And they could move their paddle back and forth, and they could feel all the changes that we're making in amplitude and frequency. And then they were tasked with drawing different graphs of sine and cosine of different frequencies and amplitudes. And so what was surprising about this design study was that in using this haptic feedback to render something that has no real world equivalent, we found that the success of the lesson really depended on the students' ability to interpret the haptic feedback. So the first pair of students, when they were playing with the device, they weren't really getting it. They were really confused. And we had to show them the graph so that and then it clicked for them. Then they were like, oh, that's what it's doing. But first they didn't really get it. And then after we showed them the graph and they made a connection with what the haptic feedback actually represented, then they were able to perform the task and draw different graphs of sine and cosine, etc. But what's funny is that for the second pair of students, one of them got it immediately. It just clicked for him. And then he was able, without ever looking at the graph, to explain to the other student what it meant. And together they were able to draw different functions like sines and cosines of different amplitudes and frequencies, and to explain to each other what that meant with respect to the unit circle. So I know it's a very small design study, but I believe that there is a power in haptics to tie together different abstract mathematical concepts and to help students understand them in an embodied way. Okay. So now I want to introduce the second device. And the second device was specifically designed for now teaching concepts incrementally. And this device was designed for more advanced high school students to graduate students. And so the idea of this device, Haplink, is that it does very clearly derived from the 1 degree of freedom Hapkit, but now it has been designed to transform between a 1 and a 2 degree of freedom system. And I propose that students can benefit from learning concepts incrementally and build on their device in parallel. And so because it's a teaching tool, then what you want to do is that the 2 degree of freedom version of the device pretty much falls from the 1 degree of freedom version, so that the 2 degree of freedom version is kind of like just slapping 2 1 degree of freedom devices together, so that and that constraints, at least that's the constraint that we put on each other, that the kinematics of the 2 degree of freedom device would fall from the kinematics of the 1 degree of freedom device. So we chose a serial mechanism. Now the challenge here is that how do you design a serial mechanism that can use pretty inexpensive motors? So for that, we needed that one motor not carry the weight of the other one, as is done with a normal robotic arm. And so we developed a new mechanism that still has the simple kinematics, but leaves both motors grounded. However, this mechanism does give the device two modes of operation. And so in the first mode, if you don't actuate motor B, but you are actuating motor A, which is the first motor, then as you can see, paddle B kind of rolls around motor B, which is static, and the angle of paddle B changes slightly as a function of that rotation. Now in mode 2, now theta B is rolling, and you can see that just the normal rolling mode with the motor and the paddle. And then these two modes are combined to render the desired motion. Now, in order to finalize the design of Haplink, then what we need to do is choose the rest of the variables, which are the length of its links, as well as the angle between those links. And changing these parameters results in the position and shape of the workspace, which is the range of positions that the end effector can achieve as it moves around. And so what we did is implemented an optimization algorithm in order to choose those parameters and to constrain the workspace to be in front of the device and to avoid any self-collisions. We constrained the box placed at a safe distance to be inside of the workspace. Now, the problem was that the underlying implementation of this analysis is not smooth. So I chose to use a genetic algorithm, and since it was so slow to run, then what I did was you do a combination of using the genetic algorithm to inform a direction of optimization and then tuning some parameters manually. And I know that there's probably a better way, but it might be interesting to then repose the problem as a convex optimization problem and then do it that way. So this is the end result of maybe a not completely optimized device, but I think it's good enough for now. And this is the footprint of our device and its workspace. And so there's a lot of, now that you made this simple robot, there's a ton of analysis that has to go into exactly how and if you can use it as a haptic device. So I'm not going to go through all of the analyses, but I wanted to just showcase one because I found it pretty interesting, which is, for example, an analysis of the workspace resolution. And so, as I mentioned, we're using pretty cheap motors, which have very cheap encoders. And in 1 degree of freedom, it's not such a big deal if you don't have your wall at exactly the same place where you had it the first time, etc., or if things shift around a little bit. In 2 degrees of freedom, it is a big deal because the forces are now proportional to where you are in space. And so one of the analyses you have to do is to really understand where in the workspace you can render different things. And so just so you see, for example, our encoders only have, within quadrature, only have 48 counts per revolution, which gives us a resolution of about 7.5 degrees in the motors, which is pretty bad. And so let's just look at the effects of these bad workspace resolution for just one area, which is pretty cool to see. So if I just want to move in area 1, and I just want to move my cursor just horizontally in area 1, I can, looking from the resolution of it, the scale of it, it seems that the resolution might not be that bad and that I could just filter it. However, what's important to note here is not so much the scale of the resolution, but that it has distinct shapes. And so if I were to just render a wall in that area, those shapes, once I convert them to forces, are going to be something that I can feel. So if I just render a horizontal wall, then my user is going to be able to feel those distinct shapes as little bumps. And so basically, now I need to know that this is going to happen so that I can compensate for it. So then there's a lot of other analysis that has to go to it. So we have to make a software that would inform us if I want to render virtual environment blah, where in the workspace and how in the workspace is it adequate to learn it. You want, basically with haptics, you want to do as little filtering, etc., as possible, because those introduce other dynamics that you're also going to be able to feel. So that's just, yeah, comment. And then, so we've used Haplink in the classroom. One of the uses was done at Stanford. What we wanted to find out is whether, so just as a backup, Stanford has these undergraduate seminars that they do. So for freshmen, just as they're coming in, and if they declare that they're interested in engineering and that's something that they want to do, then different professors run different seminars just to tip their toes into engineering. So they've never had an engineering class before anything. And usually my advisor runs a class where she just kind of gives them a small introduction to haptics. And so we wanted to do whether now using this device that could do incremental learning, whether we could actually teach them more advanced concepts. And so we did use the device. And so we used the 1 degree of freedom version of the device, taught them kinematics, and then taught them how to render very simple 1 degree of freedom virtual environments. And then we had them transform the device into a 2 degree of freedom device, taught them the Jacobian and how to render 2 degree of freedom virtual environments. And it worked out pretty well. Then at the end of the class, the last 2 weeks, they spent them doing a class project. And these are some of the examples. So for the class project, they also create their own applications. This team, for example, chose to do a game of operation. And so through 3D printing, they just changed the handle of their device and they added some tweezers and a force sensor and a vibration motor. And then they made this environment where you could go around. And if you try to grab objects, if you didn't grab the object properly, you would get a vibration and you get the gist. And then this team actually really impressed me. What they did was they made a gear shifter. And so what happens here is that they have 6 preferential positions in which they implemented force fields. And we didn't teach them force fields, but that was awesome that they taught themselves how to do force fields. And then you can move the device around if you press on the clutch, which has a little force sensor. And now here at CMU, we're also using it during the pandemic. Yay! We'll see how it goes. So we're in week 4 now of the quarter. And so students so far, we shipped them the kits, and then they assembled their 1 degree of freedom device by themselves so far. And yeah, in a couple of weeks, we'll move on to teleoperation and 2 degrees of freedom. So we'll see how it goes. All right, and now the last device is quite different from the other 2, and I just wanted to talk about it because I feel like it's another very interesting application of haptics. And this third device is now a set of tactile haptic buttons. So before we were talking about just kinesthetic devices and giving forces, this one is a little tactile haptic device. Now, the inspiration for this device came from the fact that in recent years, neuroscientists and education researchers have showed that the neurobiological basis of mathematical cognition involves complicated and dynamic communication between a lot of different brain systems. And one very interesting example of which is the way the brain uses representations of fingers to do mathematics. And in particular, in young children aged between 4 to 7, it's been shown that finger representations are somehow connected to math learning. And it has been proving that mathematics learning is increased when fingers are used to the development of math. Some studies have specifically correlated this increase in math ability to something called finger gnosis. So the way you test finger gnosis is like an awareness of your fingers. But I think the most illustrative understanding of finger gnosis is by understanding how one tests for it. And so for very young children, what you do to test for it is you cover the child's hand, and then underneath the covering, without them being able to see, you touch one or several of their fingers. And then you ask them, which finger did I touch? And based on their ability to be able to answer that question, you give them a score on how good their finger gnosis is. And so some of the researchers that have studied this effect and have studied finger gnosis use activities to develop finger gnosis, such as following a line with your fingers, touching different colored circles on a board. And so what we saw is that clearly the sense of touch is being used in some way. And so we proposed that an interactive haptic device that could exploit this connection by encouraging simultaneous finger movement, feedback, and math activities. And so we, with the aim of further understanding this phenomenon, we designed this device, which we call HapCaps. These are just haptic buttons that can be programmed to give tactile haptic feedback in the form of a vibration in response of a finger press. So each button is composed of a color sensor, which can tell which finger is pressing the button, because the users are wearing a glove with colors on it. And then it has a vibration motor to give the haptic feedback, and a combination of a force-sensitive resistor, a spring, and an extruded feature to act as a button. And so the idea is that now a user wearing that colored glove will touch a button, and then the color sensor will inform the whatever is running the software which finger touched the button, and then the software can make the decision whether to give haptic feedback and what type of haptic feedback to give as a response to that press. And so now what we wanted to do also was tie in numbers as well into the device. And so what we did is then we designed a system with 10 HapCaps arranged in a number line, and then we mapped each finger to one of the buttons, and each button and finger to a number. And so that way students could be answering questions on questions that were being asked through a computer using their fingers. This is an image of the final system. So you can see here it has the 10 buttons. And then I guess the important feature here is just to keep the electronics as far away from the first graders as possible. We also designed a software that incorporates mathematics questions that were specifically designed by Professor Joe Bowler in the School of Education at Stanford to to promote visual thinking and target several brain areas. And the software allows for the questions to be answered with our device or using a mouse by pressing on these buttons. And it also has other features such as reading the question to a student if they can't read, or they can also ask for help, and then the software will show them how to do a sample example question if they don't know how to proceed. So the first thing we did with these devices was in 2018, we ran a pilot study over 4 weeks in which we took one first grade class with 19 students and we divided it in two, and half of the students did activities with the HapCaps systems and half of them with the computer. So from now on, I'm just gonna call them the HapCaps group and the computer group, okay? And then our main, what we wanted to learn mostly from the pilot study was, number one, can we use these systems in a first grade classroom? Like, are they appropriate to be used there? And number two, we wanted to get some information from pre and post test to be able to power a longer longitudinal study. And so what we learned from the study was that, yes, we could use our devices in a first grade classroom. However, these computers were definitely not powerful enough to encounter first graders and survive. And so we needed to make our computers better. And we also learned from a power analysis that we needed to have at least 24 students in each group in order to be able to get results of any statistical significance. So then now in the fall of 2019, a year later, now we ran a longitudinal study with 92 first graders. And this study was done over 8 weeks. So this is the outline of the study. It was composed of 5 phases. And so in weeks 1 and 2, we pre-tested all of the students, both in math and in finger perception. And then weeks 3 to 10, they did math activities for twice a week over 8 weeks. And then the last 2 weeks were also done to post-test the students, using the same methods as were done for the pre-test in order to be able to compare them. So the math test was a paper and pencil test in that with activities very similar to the ones that they learned during the math activities period. The finger Gnosis test was a test based on those done by all of these researchers that have done research in finger Gnosis. And the idea is that a student will sit on one end of a table and then stick their hand through a box so they cannot see. Cannot see their hand, and then 2 researchers sit on the opposite end of the table, and then they proceed to touch one or several of their fingers with a soft brush, and then they ask the student, which fingers did I touch? And without moving their hands, however many they can get correct, then that's how you score on their finger perception. Now, these are our results from the study. As you can see, we did see an increased improvement in math from the HapCaps group compared to the computer group. Specifically, the mean improvement in math was 7.9 points versus 2.8 points for the computer group. And we also ran a 2-sample t-test which did show that the 2 groups are statistically different at the 5% level with a p-value of 0.0015. So we can conclude that the HapCaps group improved more in math than the computer group. Then we also, now the results from the finger Gnosis test are here. And this was a little surprising, and I will talk about this in just a second. But we did see more improvement in the HapCaps group than the computer group in finger Gnosis. Specifically, we saw a mean improvement in the HapCaps group of 5.3 points versus an improvement of 3.7 points for the computer group. However, when we ran the 2-sample t-test, that showed that the 2 groups were not statistically different at the 5% level with a p-value of 0.22. So we cannot actually conclude that the HapCaps group improved more than the computer group. Then the other analysis that we did, because with the other piece of information that we had was all of the answers, the recorded answers to the questions that the students did during the 8 weeks of activities. And so what we chose to do in order to analyze this time-based data is we fit a Bayesian knowledge-tracing model to the data. And so a Bayesian knowledge-tracing model, what it is a hidden Markov model in which the observed state is the answer to the questions, whether they get it right or wrong. And then the hidden state is their knowledge. So whether they know a particular skill or not. And then the model will also output the prior probability of how much they knew before they started, and the transition probability, which is the probability of learning, of transitioning between a not known state to a known state. And so what this model told us is that it actually concurred with the results from the pre and post tests. It fit a lower prior probability for the HapCaps group, which was in agreement with the lower score from the HapCaps group in the pre-test. And it scored a higher learn probability for the HapCaps group, which also concurred with the fact that the HapCaps group improved more than the computer group during the time period. And so from this, I just go back to this slide because so both of the HapCaps and the computer group receive the same visual and auditory cues. And so we can, and so the sensory motor aspects of moving the fingers and receiving haptic feedback, we think are pretty confident that they did have an effect in improving the math scores. And then based on prior research and our efforts to design the devices that encourage all this finger movement and that provided tactile feedback, we had hypothesized that changes in finger noses would correlate to our measures of mathematical ability. However, we did not see a significant difference in finger noses between the HapCaps group and the computer group. And so these highlights something that we feel has not been previously shown, and that is the importance of finger number relations over just numerical training without finger associations and over finger gnosis alone. So in conclusion, I just wanted to say that there is still a ton of work to be done. For example, with Hapkit and Haplink, to really understand the role of haptics in STEM learning and to conduct different experiments into understanding the role of haptics in different subjects, so physics, biology, chemistry, etc. And what benefits from haptics and what doesn't benefit from haptics, and really conduct these studies in classroom environments. Then for HapCaps, there's still a lot of work to be done in really understanding the underlying mechanisms for this connection between finger use, finger representations, number representations, and learning for very young children. And I guess the concluding message that I want to leave you with is that I believe that there is still great untapped potential for haptics in learning, in exploring, touching, moving, and we hope that this work will help to get these devices into classroom and to perform more experiments that could improve education. And I just want to acknowledge the fact that all of this work was done under my previous awesome PhD advisor, Alison Nakamura, and with a ton of awesome collaborators. And the work was funded by the NSF and the Human Center for Artificial Intelligence at Stanford, and also private donor money. And with that, I will take any questions.
So everybody, let's thank for the good talk. You can hit the clap button or show it or whatever. Just to keep things a little streamlined, I would ask that you all either you raise your hand, or if you don't want to speak out loud, you put your questions into the chat and then I'll read them off for you. Normally I would give your cat the first questions because it raised the interruption and kind of clearly wanted your attention right from the start, but I don't think it's going to ask a very interesting question. So
did you see her jumping in the background? It was awful.
If someone have a question, please raise your hand or drop it in the chat. Henny.
Thank you, Melissa, for that awesome talk. And very inspiring to see a study with 90 children over 8 weeks. Like, my head hurts just thinking about the logistics of that.
I have hives.
Pre-traumatic stress. So you briefly touched at the end on this need for doing more research on what it is that makes a good haptics education problem. So do you have a sense of some general principle that we could apply that would say this kind of educational problem is really well addressed through haptics?
Yeah, that's a very interesting question. I would say in my very limited experience, it is very important to keep in mind what the capabilities of the devices are. And so I believe that what has been at fault in some of the studies that have been conducted is that the device wasn't really appropriate for the type of simulation they were trying to do. And so there's a lot of principles, for example, in psychophysics, not psychophysics, in neuroscience, in how, for example, like if you want to render a simulation of an inclined plane, then perhaps the best device for it is not something where you're just like pulling back and forth, but perhaps it's something that actually allows you to have a real embodied interaction with the inclined plane, right? And also another important thing to remember is that, yeah, haptics devices are not awesome yet. There's still a lot of work to be done in that, which is why, I mean, not only because I really like math and I'm really bad at math, so I want to be better at math, I focus on math, but I feel like just rendering abstract concepts that don't really exist is a tiny bit easier, in the sense that the user is not expecting it to feel a particular way. Like you can really just come up with your own embodied interactions. But
Okay, do we have other questions? So I have a question. I'm going to use this opportunity. There's all these stories of music having a strong, tight, relationship with math. And then, of course, there's always correlation, causation, and all that sort of thing. But one of the things that occurred to me during your talk is, in music, the rhythm, the beats, the fractions, that is all reinforced by the physical actions of the musician's fingers. And so,
yeah.
Is this like theoretically a possible influence on the connection between math and music? Is the physical feeling that they're getting through the playing of the instrument?
I think so. It's funny because the reason why researchers started studying these relationship between finger gnosis and math learning was because of this effect. Everybody knows that if you play music, you're using your fingers, and somehow you're better at math. And that is still not very well understood why. And so that's why that's why a lot of people are doing research in this space. So I do believe that, I mean, there's this theory where people think that you actually have a region in the brain that's basically like a picture of your hand. And then there's people who have done MRI studies, and even people who are more advanced in, right, like who are like in university, etc. And then they put them through the MRI, and as they're doing a math problem that has nothing to do with their fingers, they're not really counting on their fingers, this area of their brain lights up. And so, of course, I mean, always when people say like, oh, this area of the brain is specifically a picture of the hand or something, you're always a little skeptical, right? And you're like, well, I mean, do you really know? But there seems to be a strong connection between fingers and math for some reason. Yeah.
So this raises the next question from a robotics perspective is, if people have these different levels of perception capability in their fingers, if you're interacting with a robot that has some sort of tactile expression or haptics expression, and like we all talk about robots tuning their performance to the user, you could imagine the robot tuning its interactions with its physical interactions with people based on like asking you a quick math question at the start. Be like, oh, I need to be a little more forceful with you so that you can actually feel this,
Oh, I see.
That's probably an extreme example, but is that like,
Yeah.
is this the sort of thing that we might actually, be thinking about over the long run? Is
I don't
inferring a person's starting state in terms of haptic interaction based on other measures?
I don't know. I honestly don't know. I'm not so sure that it is like your actual perceptual ability what gives you the better math sense or not, as opposed to the fact that if you use embodied interactions with an abstract concept, then you actually can ground those concepts in your body and in movement, and so you give them a real representation as opposed to them just being something over there. Yeah.
Okay, Keen dropped a question in. For those who can't read the chat, it's been recorded, for recording, I don't know if you can read the chat. I'll read it off for you.
Thank you.
Do you think examining skilled athletes, artists, or musicians for what auxiliary skills they excel at would be a reliable indicator for predicting which problems can be addressed with haptics-enabled kinesthetic learning?
And for that, I just want to ask, then does this mean for learning that particular skill that makes you a great athlete, or like for learning chemistry, for example?
I don't know if Keen has the
Yeah.
microphone on or not. Why don't you just answer
Yeah,
answer
I
one of
think
them, and then
I think
and
I'm
then if
going
we're
to I'm going to assume that it's to learn that particular skill set. And I do think there are researchers that are analyzing athletes' movements and the way they do things, and specifically which muscles are the ones that get fired up in order to actually analyze what exactly it is that they're doing. And so this is, in a sense, haptic and kinesthetic learning. I'm still not sure about what the best way to learn that is, though. I have seen both approaches, one in which instead of showing a person and guiding them through the right movement, trying to get their muscles to the right movement, I've seen that approach. I've also seen another approach, which is instead of posing that movement and making it harder for the person, and that actually helps you achieve that better. Yeah, but I'm not so well versed in that. I'm sorry.
Okay, Sarah.
Yeah, thanks, Melissa. That was awesome.
Thank
So quick question on going back to the hardware.
Yeah.
So you mentioned you feel like haptic devices aren't all that yet. What do you
Yeah.
feel, what do you feel are the missing parts? What needs to be improved really on the kind of mechanical or electromechanical design side?
Yeah. So do you mean in kinesthetic or in tactile haptic devices, or do you want me to comment on both? I can also do that.
Both.
Okay.
Yeah.
Yeah, absolutely. So I feel like so far the main application for haptics is still hasn't been done. Because of that, what hapticians have done is really adapted their devices to the actuators that are there. And so a lot of what we do, for example, in terms of kinesthetic devices, even though we're in the end doing linear movements, we use rotational actuators because that's what the cheapest thing that's out there, right? And linear motors really have a lot of friction, etc. And so the actual great kinesthetic actuator for haptics still doesn't exist. So we just do the best we can with what's there, and then we adapt our little joints and etc. to fit that. In terms of tactile haptic devices, there's just a million things to do. Like just tactile haptic devices don't have the spatial or signal bandwidth that we can sense. That's just in a mechanoreceptor part. And then there's also the whole thing where we actually can sense moisture, and based on moisture, we sense different signals. So that affects a lot the performance of our mechanoreceptors. There's also temperature, and that also affects what we feel. And so that just a good haptic actuating material still doesn't exist. There's so much work. You can solve it though.
It was a leading question. That's no good. One other just comment is actually I have a kindergartner and a second grader, and they learn reading through tapping. So they tap out sounds and then like make the word. So they'll do C-A-T, but they'll go k-a-t and then something like this.
Wow.
So they're doing I mean, there's some theory behind it that I'm not familiar with, but it's an interesting kind of non-math application that your HapCaps made me think of.
Yeah, no, I had no idea that was a thing. I'm gonna look into it. Thank you.
Yeah, I can find out from their teachers what I'm sure there's some body of literature. I'll send it to you. Thanks.
Thank you. Emma, you're up.
Thank you so much, Professor, for such a wonderful talk.
Thank you.
It was really, really cool to see your work. I'm actually a TA with Professor Bergbrighter this semester, and we used your Haplink as an example of a two-link system this week. So we got a little meta. We like analyzed your teaching tool for teaching dynamic systems. And I think actually some of our students are here on this call today too, just to see, the breadth of your work. And just from my own perspective, writing up this recitation and using your Haplink as an example, I was curious if you could talk through maybe a little bit about some tricks or tips you have on how do you come up with 8 weeks worth of material to teach your students, and how do you decide what you want to include and
like just with the device?
Sorry?
Like about the device, or like in a specific class on something?
Yeah, exactly. Like with your Haplink system, for instance.
Oh, okay. Yeah, so right now I use it to teach a class on haptics itself. And so what I go through is I teach them first kinematics and the kinematics necessary to analyze the device, then the dynamics necessary to analyze the device, Then I teach them what a haptic virtual environment is and how to render it. And then we also are going to go through teleoperation, so how to hook up two of them and the necessary controls for that, and transparency and stability. And then after that, going to 2 degrees of freedom, and then also with kinematics, dynamics, controls, and then rendering. So the rendering of virtual environments, all the algorithms for higher degree of freedom devices are actually pretty complicated. And so yeah, then going through that takes a while.
Very, very cool. So your course is able to touch on and sort of build students' intuition for a lot of these aspects like kinematics, dynamics, controls, and then
Yeah,
onwards. Thank you so much.
thank you.
Okay, are there other questions? We're coming up right at the 4:30 mark, so this is timing out perfectly.
Nice.
Okay. Once again, I want to thank Melisa and everyone for this interesting talk and interesting questions. And once again, thank you. And I hope you all enjoy our first weekend above 32 degrees that we've had in a while. And we'll see you all next week. Thank you very much.
Thank you.